Okay, good morning, good afternoon, and good evening, everybody. Welcome to this IAHR webinar on a newly published monograph on flood risk management. I'm Damien Violot. I'm chairing the task force of IAHR on the new series of water monographs. And as an introduction, I will say a few words about this new series of monographs. So, Estibalis, would you allow me to share my screen, if you please? Okay. So now you should see my screen. Can you just confirm me that it is the case, Estibalis? Thank you. So what you can see here is the web page of the IAHR Water Monograph series that you will find easily by writing IAHR Water Monograph series on Google. And you can see that the monograph that we are talking about today appears here, but you have already 4 water monographs published during the past 2 years. All of them, importantly, are open access. So we decided to start this new series of monographs 3 years ago with the aim to allow some authors to publish some work very focused with length between 50 and 150 page. So that is to say, between a journal article and a book. All of them are for free, and you can download them from this page. So just feel free to go there and to see if you are interested in looking at these works. Also, if you want to contribute by proposing a new title, you just have to contact either Estibalis or me, and you'll find easily our web address from the IAHR website. Okay, so today we are talking about a water monograph titled Practical Flooding Risk Assessment for Development Projects under the supervision of Alastair Barnett. And all the authors are going to introduce this work. Also, before we start, I would like to acknowledge the sponsor of this monograph, since we are working under open access conditions. All the monographs have a sponsor, and this is Hydra Software Limited, who is sponsoring the presently presented monograph. Estibalis, do you think this is okay as an introduction? All right, Alastair, do you think it is okay as well?
I'm fine with that. Thank you.
So I start talking when you want.
Thank you, Damien. First of all, I'd like to make a special welcome for our guests in Peru. We were quite excited to see how many people from Latin America wanted to join us. And in Peru, this is a heroic thing because they're having to get up in the middle of the night. So welcome. Practical flooding risk for assessment for development projects is the monograph as mentioned. And I'll move on to the next slide, please. Can I have the next slide, please?
Estibalis, I think that I can see the slide number 3, but it might be better if you put it full screen. Okay. Alastair, is this the slide you wanted to see?
No, I can't see it. I can see a slide picture of some sea. This is from my PowerPoint.
I do see the slide titled Development Projects Risk Assessment. What about you, James?
Oh,
I can see the full screen slides now. Previously, it was the PowerPoint slides.
Okay. Alastair,
So-
can you see the full screen presentation now?
No, I can't. It's not there. Perhaps I should. Very well. I will read from my notes here. The development projects risk assessment. Chapter 1 of the monograph introduces an engineering view of flooding risk assessment when planning a development project, such as a hospital, a hydropower station, a housing estate, or a shipping port. Before construction can begin, practicality requires project finance to be found, and funders need assurance that the proposed project site offers security against threats that may compromise their investment. Insurance is part of the answer, but at an affordable cost only when international reinsurers can be convinced the project is well designed to withstand all but rare exceptional events. So insurance is a key part in any project practicality. Until the end of the 20th century, this link between flooding risk and insurance assessment was barely acknowledged because engineers and insurers both relied on climate stationarity in their standards. Now, if we move on to the next one, Hurricane Katrina. This complacency of everyone thinking, well, stationarity is going to make us all agree, received a severe jolt in 2008 when Hurricane Katrina caused unprecedented flooding damage in and around New Orleans. Trends such as rising sea level, increasing storm hazards, and sinking ground levels through continual pump drainage had all been well documented, but have been no one's responsibility to look at the combined effects of these hazards.
Excuse me, Alastair. Excuse
Yes.
me, can you redirect your sound to the micro? Otherwise, it's not easy to hear you.
I'll have to pick up my paper then. Right. I hope you can get this slide projection onto my screen soon, because otherwise I have to read from the side all the time. So hydraulic engineers of the Aquaterra International Advisory Committee, led by Dr. Gayla Rodenhouse, then made contact with reinsurers led by Munich Re. In fact, I was the one that made that contact through my contacts with Munich Re and close collegiality with Gayla Rodenhouse. I was able to make that contact, and the response was that if both engineering and actuarial approaches were truly evidence-based, then they should converge on the same answers. So that convergence was agreed between the reinsurers and the engineers, that provided everyone worked from evidence, then the evidence should point to the same answers. A direct outcome of relevance to the monograph is guidance-based analysis. I seem to have suddenly got my screen. Thank you. All right. Put that away. So this is an example of evidence from the benchmark of 3D scalar model validation, figure A4, from Appendix A. And this is Appendix A. I'm referring, of course, to the monograph, which is available for free download, those of you who have not already done so. It shows an example of data from a gauging station on the Opanuku stream, a largely urban river in a hilly catchment. 2 flood hydrographs are shown as computed using 3D scalar modeling at OLOS version 5, that's a Hydra software product. One dates from 2006, and that's OPA 06Y, and the other one 2008, OPA 08Y. Each predicts a loop rating curve and both are plotted against flows gauged between July 1999 and April 2012. So you can see the various times there where the recordings were made. The falling limb curve for the 2006 flood gave a calibrated springtime Manning N of 0.045, and for the 2008 winter flood, the Manning N calibrated to 0.04, 0.04. This 3D validation is part of an urban flood study commissioned by the former Auckland Regional Council, and they adopted this as standard. This evidence benchmark as standard was adopted by that council. Next, please. So does your present model work? If at certain successive moments your model can match both the level observed along the channel and the 3D scalar discharge measured through a specific cross-section at several such selected moments, then that model is evidence-based. If there's a good match throughout, then the model results and laboratory or field measurements are mutually validated. Field measurements validate the model, and the model validates the field measurement. Next. This concept also requires that modeling based on observed levels and modeling based on observed flows must produce the same answers for both level and flow. Either projecting from level boundaries to find flows or projecting from flow boundaries to find levels must give the same answers for the model to be valid. And Appendix A of the monograph gives that. Next, please. If there is no match, then the observations and measurements may be defective and therefore invalid. Don't just assume that the model is wrong. It may be the observations that are wrongly observed. If you can't rule out there's any problem with the measurements, then no conclusion can be drawn about the validity of your model. So next, please. As an example, a range of flow measurement techniques specified below. I'll give several examples of that. Most of the 3D verification techniques rely on Leonardo's principle of conservation of volume. Of course, that's Leonardo da Vinci who first famously produced that principle. For instance, cumulative volumes may be measured and compared in a laboratory discharge pit to give a measure of mean inflow over the previous time interval. So next, please. I'll like to go through these quite quickly. So surface level measurement, this is a typical long-term recorder, and the verification goes to a survey benchmark. Next. Next, please. Yes, sorry, could you go back one? Or not possible. All right. Yes, that one. Yes. So if you have control of the river, this is hydro schemes, they are able to largely cut off the flow, then you can safely get into the river and make the measurements manually. Next, please. Or if you have limited requirements for the wave height, if the wave height, mean height, and arrival time are the main things model calibration requires, then you can save installation time, because observation towers and so on take a great deal of expense, whereas you can throw up a bit of scaffolding like this and bang in some staff gauges in very quick time. So that one was done that way and was quite satisfactory. Next, please. Another technique is dye dilution, and that is very good for where there's heavy rock armor and much of the flow is passing between the rocks, because you can't get in there with typical velocity measuring instruments and see what's going on, whereas the dye dilution gives you an accurate answer for the total flow. Next, please. And the laboratory, this will be familiar to many of you who work with laboratory measurements. a typical electromagnetic flow meter, and then you verify that by using a discharge pit downstream end. Next, please. In remote sites, and Tarawa Lagoon is about as remote as it gets. It's right in the center of the Pacific Ocean, and but we still need to measure discharges in and out of the lagoon there. And we found that green coconuts are ideal because they're locally available, cost nothing, and they have a density for 95% submergence. So they're not badly affected by wind, although there was no wind on the day we were doing the measurements there. Next, please. If conditions are dangerous, and certainly a 5,000 cubic meter per second flood is dangerous, you don't want operators anywhere near the water. So they stand safely on the bridge and pilot this drone, which is not an aerial drone. It's a boat-mounted drone. It is fully equipped with acoustic Doppler current profiler and so on. As you can see, they can run that around on the surface of this enormous flood and pick up a complete profile in a very short time. Next, please. What if you can't model that match the verified evidence? So the Monograph offers 2 verified 3D scalar benchmark options. For construction channels, see Chapter 8. For natural channels, see Appendix A. Next. If your model is unable to match both benchmark results, you should ask yourself if it could ever have produced an answer matching records of a previous event. After all, a practical reinsurance company assessors will not accept your model analysis if you can't do that. Next, please. If you wish to look at the original benchmark solutions, you can download the freeware Aulos version 5 executables, and that comes preloaded with the data sets as given in Chapter 8 and Appendix A. And you can do that from that website there. Next, please. Flooding threats from the sky. You have IPC projections of climate change are of little help to engineers because they do not offer projections through the 21st century of either the 2 fundamental flow parameters, peak flows and peak flooding levels. Instead of that, we are offered projected rainfall intensities. Now, this is just the methodology that IPCC has chosen to use for doing their future projections. But we need to move from projected rainfall intensities to peak floods, and rainfall intensities are now regularly gauged in many locations, and so we can get climate variability since 1990, both within a catchment and across adjacent catchments. So next, please. At peak catchment outflows and such peak storms, a reasonable hypothesis is that an unchanged catchment will again respond to rainfall of the same intensity by producing the same discharge. So if you have an AEP, annual exceedance probability, is increasing above the stationary values as pre-1990, this hypothesis requires that the stationary rainfall intensity must become more probable. In other words, have an increased AEP. Next, please. As a worked example is given in Chapter 4, and this one is a study from Makara et al. The publication details are given in the monograph. So if you have the printed version, you can work through this and look at the way in which the calculation could be done. And then next, please. And the demonstration example there works through plots. And again, you can work through this with the help of the monograph. Next, please. But we need flood frequency analysis as part of the calculation. And this picture of diminishing return period for the same peak flood discharge cannot be completed without access to flood frequency analysis on the river where the peak discharges are to be projected. Now, this piece of the puzzle is now coming available only after a lengthy research program led by our Australian engineering colleagues. One of the leaders of this research was Dr. James Ball, and I now hand over to him to tell us where we can find the results.
Excuse me, James, if I can interrupt just for 1 minute to say something important to the audience. I forgot to say that if you have any question to the speakers, they will have no time to answer your questions during this webinar. So please write your questions in the chat window, and the IAHR Flood Risk Assessment Committee will manage to answer the questions through their websites within a few days. Thank you very much. So James, now you can go.
Thanks, Damien. I'm just making sure I get the right slides up. I assume everybody can see the slides. I'm from UTS, and I'm going to talk primarily about Chapter 3, but a little bit about Chapter 4, and we're going to be talking about flood statistics from a design perspective. And I want to distinguish between flood design and flood analysis. Design involves the prediction of the flow rate, the levels for prescribed or desired annual exceedance probabilities. And I'll avoid the return period concept, but I'll give reasons for that later. Flood analysis, on the other hand, involves replication of an actual catchment response. The two are not the same. We complicate matters by using the same tools, the same models and everything, but design and analysis are not the same. And the primary difference between the two is in design, we're trying to predict a statistic. That is the design flow that has a given exceedance probability. It's not the outcome of an event, it is a statistic. What we need to recognize also, when we design infrastructure or we're doing a flood design, we are also accepting the probability that a hydrologic failure will result when a larger flood event will occur. In other words, we're doing a risk assessment to allow for larger events. Hydrologic failure does not mean the infrastructure will be destroyed or damaged, but it fails to perform the surface for which it was designed. So in many cases, your flood overload problem is one of the major issues. In other words, working out how your infrastructure fails. What is the expectation? And we'll use 70 years period, that being, or used to be, the life cycle of a human. But in that period, a 1% or 1 in 100 year event, you have a 50.3% chance of it occurring in that 70-year period. In other words, it's a 1 in 2 chance of it occurring. At the same time, you have nearly a 1 in 6 chance of it occurring twice. And we can go through them all, but if you go to a 10% event, you got a 99% chance of it occurring at least once. Why is it not 100%? There is always a chance it will not occur in that period. You're dealing with statistics, not determinism. We can actually go one step further and even then work it out. And there's a simple relationship there, and that's in the monograph. for a stationary event, stationary system, working out the expectation of an event occurring for a given probability and design life. In Australia, quite often we look at the design life as being the land use and not the building. So once you have a land use that allows buildings, you can replace them quite easily. Okay, we can also do that under climate change with changing annual AEPs. So you can maintain the expectation of events occurring under changing climatic conditions. So you can work out what the AEP at the onset of the period is and what it should be at the end to have the similar expectation. However, social equity, particularly intergenerational equity, raises its head because you do not have an equal chance of that failure occurring during the life period of that infrastructure. So there's a major social issue there. Okay, what are we going to do? Essentially, we're going to look at if suitable data is available, we're going to undertake some form of pattern analysis, typically statistical. If suitable data is not available, we're going to do the traditional engineering approach, and we're going to generate suitable data. And that generation will typically be with catchment models. We're then going to data mine that available data using statistical models for estimation of the desired flood quantiles. We can usually express them in annual exceedance probabilities, return periods being somewhat equivalent to the inverse of the exceedance probability, can be used if the climate is stationary. If the climate is not stationary, return periods fail. They no longer work. And your annual exceedance probabilities are probably better. I must have unmuted myself. What are the steps involved in undertaking the analysis? The first one is to record the flood series. We then plot the annual exceedance probabilities against the discharge. That's referred to as plotting positions. We then fit a statistical model to the series and determine the confidence of our predictions. Note that we are fitting probabilities against discharges. The reverse, while we do it quite often, is not statistically correct. Okay, two types of flood series that are commonly used. The annual maxima series consists of the highest event in each water year. I use the term water year rather than calendar year because there are many places around the world where the monsoon or wet period goes over the change in calendar year. So you select a water year, typically dry period to dry period in the series, and select the highest event in each water year. The alternative is the peak over threshold series, which consists of all events greater than an arbitrary base value. Now, on the right, you have a diagram there which shows some examples. Obviously, D will be independent of A, B, and C. But in our pot series, would A, B, and C be recorded? or not, because you are looking for independence. And A and B are probably not independent. I will leave C there as a distinct argument to be had. The relationship between the AMS and the POT series is given by Langbein way back in 1949. You have the reference there. Anything above about a 1 in 10 year exceedance probability, they're almost identical. It is below the 1 in 10 year probabilities where there is divergence. Three components to fitting a flood probability model. You need to calibrate the statistical model to determine the parameter values. You then need to estimate the flood quantiles and the confidence limits. And then you need to evaluate the goodness of fit and consistency with data. And I realize I'm going through this very quickly, but we don't have a lot of time to cover things. Some of the distributions, you have the GEV, nice theoretical distribution, LP3. If you live in the US, you live in LP3 world, and log normal, if it's there's no skew to the data, and we can keep going through them all. But typically, they're the most commonly used distributions. And I've just primarily for it, because in Australia we use the GEV and LP3. They are both 3-parameter distributions. The GEV, you have a location parameter, which defines where it sits. The alpha and kappa scale and shape parameter, which defines the slope of the flood frequency and the curvature. The LP3 has a location parameter and 2 shape parameters. Very similar. Both of them can normally fit the data in the realm where you, or region where you have data, the probabilities where you have data, but they will extrapolate quite differently. And it is the extrapolation you need to be careful of. And I've more or less said that. The final thing to note, there is one thing to note there though. In any distribution, there's probably more than one set of parameters that can be fitted using the available data. So there is uncertainty about the data itself and the parameter values themselves, and that can be quite important in determining your prediction limits. Typical methods used to fit the parameters include method of moments. Now, we know that is biased to very frequent events where most of your data is, so it will fit where the majority of the data is best. We can look at method of maximum likelihood, and we can use Bayesian inference to try and remove bias and give equal weight to all probabilities. Once again, refer you to other documents and the monograph for more details. One of the important things is being able to determine the plotting position, and that's usually done by looking at that general equation on the left. Or most of the plotting positions will collapse to that equation. If you use alpha equals 0, you end up with the y-ball plotting position. 0.4, you end up with Kinane's position, plotting formula and plotting position. That Kinane's formula is very much used in Australia, but it's used because it's unbiased over a range of different statistical models. So it fits and works well with a large number of alternative distributions. You end up plotting it and you end up with a plot like that. In this one, the circles are the recorded data. The solid line is the frequency analysis, and the dashed lines are your prediction limits. So if we look at that and we look at, say, the 10% probability, 1 in 10 year event, we're looking at a range between 500 cubic meters per second, or as the most likely value, but a range between 1,000 and about 300, I would say. So you do have a wide range, and this is why you need more and more data. Because most of them are 3-parameter distributions, you are really looking for more than 70 years of continuously recorded data. Thank you for that. And just a few little flood photos to keep things going. And the one on the left is one that sort of shocks a number of students. You have a treatment plant, sewage treatment plant, wastewater treatment plant, whatever you want to call it. They're always in the low area of the land. What happens in low areas? They flood. And that's what happens when you get a flood occurring. So at that point, I will pass back to Alistair and stop talking.
Thank you, James. Coming back to flooding threats from the sea, we had flooding threats from the sky beforehand, but the flooding threats from the sea are equally dangerous, certainly in coastal areas, and they have to be taken into account sometimes in combination with precipitation-based flooding. The two may be together, but you need to be able to provide some kind of a boundary condition which gives you the change in the flooding threat from the sea in the long term. Again, IPCC projections of climate change are not much help to engineers because they simply they don't offer the two fundamental flow parameters, peak flows and peak flooding levels. Instead, we're only offered global projections of mean sea level. Next, please. Yet such projections do offer significant evidence the sheer scale of coastal flooding risks may soon make them uninsurable. This comes back to our problem with insurance. Our Japanese and New Zealand co-authors live thousands of kilometers apart, yet we're finding ourselves on the edge of the same Pacific Ocean, with comparable accelerating sea level rises at harbour gauges at two extremities of the largest geographical feature on Earth. That is, of course, the Pacific Ocean. Next, please. So the IPCC projections can be shown to match two distinct phases of recorded Pacific Ocean level rise behavior. From 1950 to 1990, sea level rises could have been projected from a model of a steady rise, which was slow enough to be relatively benign. We've lived with that for something close to 70 or 80 years now. If this continues to dominate until about 2050, the exponential growth phase from 1990 will remain subdued enough for us to continue projecting within a narrow range for one more building lifetime. That's roughly 50 years is the typical life we expect from our buildings before we decide they're out of date and pull them down, build a new one. So we can expect planned coastal infrastructure levels to continue to be insurable for one more building lifetime. Next, please. However, continuing rapid improvement on the success rate of our civilization minimizing carbon emissions, in other words, the COP talks, will have to be still successful and, in fact, with improving success rates if this projection is credible. If we fail, and I mean the COP talks and all of us as a civilization, projection of sea level rises in the lifetime of our grandchildren will have no recent historical trends as precedents, and publicly available reinsurance will become a lottery with very few winners. So I think even now we're starting to give up on some insurance and reinsurance. I think that's too soon yet. I think we've got another generation of buildings in front of us. But that's it. Next slide, please. So this is the Pacific Ocean as fitted with the BSP model, and this is all explained in chapter 7. We're not yet got the hockey stick, but we do have this linear rise transforming into an exponential rise around 1990, and we can still plan on that. The actual plot there comes from Japanese study, and so we can plot on that. Next, please. So in summary, projections of sea level rise can now still be backed with enough evidence to design insurable projects, as demonstrated by current practice in Japan. A leading part is being played by specialist co-authors from Tohoku University, Fumihiko Imamura, Kwanshai Pakuksong, and Anawat Supasri, especially with the tsunami design practice. Anawat will be presenting on behalf of the Tohoku team.
Thank you so much. Can I start? Okay. Can you see my screen? Hopefully it's okay. Yes. Thank you so much once again for the opportunity to join this series and to share our chapter during this webinar. I'm Anawat, and I would like to give you some ideas on behalf of my team in Tohoku University on our Japanese practice on tsunami mitigation. So we'll couple with zero rise, which I will speak in the later part of my talk. Before that, as you know, that Japan, we experienced series of tsunami in the past. For example, in 869, this is the oldest tsunami that we have documented, which is create very devastated impact in our region. And since then, we had a big tsunami from earthquake in 1611, 1896, and 1933. And on the other hand, we also have several another smaller tsunami from earthquake, let's say magnitude of 7.4 to 8.2 every 40 years. In Japan, the tsunami also really depends on the location of the earthquake and also the location of the area. Like, for example, in the north of Japan, they experienced more than 10 meters of tsunami in the past. But like in Sendai, because we have this peninsula, which help protect the tsunami from the north. So you can see quite different in the tsunami height distribution, even from the same events. In Japan, how we mitigate tsunami. This is a list of how we adapt. So in the past, of course, the progress of construction is not that modernized like now. So we start from moving to the high ground. But for some events where we have it's quite sequent, so we start to combine between moving to high elevation and also the sea wall. And then since 1960, where we have tsunami from Chile, which travel from Chile to Japan after a day. It took about 1 day, and there was no effective warning at that time. So they start to build more structural measurements since then. But since 1993, when tsunami arrived, only few minutes after earthquake, so they start to realize the importance of combining structural and non-structural measures. And we also changed the word from prevention to reduction, as we realize that we cannot fully protect the tsunami. This slide is to show you overview of what we have in Japan in terms of structural measures. For example, offshore, we have a breakwater. Here, this is one of example in the city. We have in Fudai here the floodgate that can stop tsunami coming through the river. We have seawall in Taro. This is a photo before 2011 tsunami. Now that tsunami overtopped the seawall and destroyed the whole village. We have also the pine forest here, hoping to also protect for smaller tsunami. But again, 2011 tsunami totally destroy all the pine trees, and also a kind of planning to ask people to live in the higher elevation. These are some photos of a typical example of when tsunami overtop the seafloor because of higher velocity that increase at the backside or landward of the seawall. It caused strong turbulence and caused strong erosion behind the seawall. So this is what we can always seen after the tsunami in 2011. So based on this experience, so after that we make a decision how we do performance based to determine the height of coastal defense. So we come to the idea of level 1 and level 2. So level 1 mean we will build the height of the defense as high as the tsunami that happen quite frequent. Let's say 50 years to 100 or 200 years. And on the other hand, for 2011 like tsunami like events or 2004 Indian Ocean tsunami like event, we allowed the tsunami to overtop the defense, but we make sure that this kind of failure will not happen by strengthening structure behind the seawall or behind the backwater, and make sure that we have a good evacuation planning, evacuation routes or the shelters. And this is to show also depends on the topography. Like in the north of Japan, we have mountainous area. So we typically after tsunami, we ask them to move to the high location, and we top up the land next to the sea. But for like the city where I'm living in Sendai, we are very flat area. So what we call multi-layer countermeasure. So we built many layer. We used to have seawall, pine forest here and highway here. So after tsunami 2011, we increased the land elevation here to be another layer. And to do that, again, for us as engineering, we do several types of simulation with changing the height of the elevated road, and we comes up to the idea that, okay, if we have the tsunami flow depth less than 2 meters, the building damage might not be that large. So we come up with our solution that 6 meter is the best height to be elevated. I'm thinking of the construction costs and etc. reasons. And in Japan, for tsunami warning, we start from 40, 50 years ago or more than that, but it took about 20 minutes so that the first tsunami warning message can be disseminated. We use assume many earthquake fault parameters all around the country, and we pre-simulate many cases in the database. And when the earthquake happen, we will take from the database the closest earthquake parameters, and we release the warning. This is how we work. We still cannot do by real time. But because of these two examples that tsunami arrived within 7 minutes or 5 minutes, so right now we still sticking to we have to release the warning within 3 minutes after the earthquake. And so we know that at that time, because of the earthquake was earthquake was so big, and the ground shaking time was even longer than 3 minutes. So we couldn't. That's why we underestimate the earthquake size, magnitude, and also tsunami height as well. So this is how we start updating the level of tsunami warning at that time. So to overcome this issue, so of course we still have to rely on the classical database system, but few years ago, the government has already completed deploying around 150 seafloor cable sensors like this figure, that these sensors can observe detect both earthquake and tsunami even like along the trench. So it's not only for earthquake generated tsunami, but for other types of earthquake, non-seismic tsunami, like the one in 2022, the volcanic eruption from the Tonga. So that types of non-seismic tsunami can be observed or monitor using this kind of system sensor as well. We also working on the social perspective. We reduce the class warning class from 8 to 5 levels to make it more simple, and we will not give a number for very big case, so that otherwise people will compare the announced number with the height of seawall in front of them. That thing might reduce the chance or possibility of evacuation or discourage people to evacuate. And connecting to the previous chapter or what that has been mentioned about sea level rise, we also have tried some examples, some case of sea level rise over top of tsunami. This is one example that, for example, sea level rise of 70 centimeters in some area of Japan. So the blue one is without sea level rise, and yellow is with sea level rise of 39 centimeters, and red one is for 31 centimeter. You can see that tsunami could go for inland, not that big, but if you do the cross section, you can, like in this one, at example, you can see that depending on the local topography, the increase of tsunami run up causing by sea level rise might be double of the amount of sea level rise itself. This is just to show you another example and how it can increase the inundation and also the tsunami heights. I think because of the time, I will skip this one. And this is another example how we can interpret this sea level rise on tsunami in the reality. Actually, I have a chance to go to this school again yesterday. This is a school where luckily, well, you can see tsunami at that time in 2011 reached to this level. And luckily, the school student and teacher could survive within this space under the roof. And so again, so if we have sea level rise at that time or in the future, such situation, it might be hard for them to survive in such situation. Or this man, he's the owner of this shop. He could survive in the second floor of his shop or house. But if we have more sea level rise, that means the tsunami force will be getting higher, or the water might reach to his second floor. And this is another perspective of sea level rise and tsunami, but not in Japan. I'm sorry, but this is another example in Macau, where they plot the relationship between the tsunami flow depths and the return period. Of the black line is in a normal case, and with sea level rise of 50 centimeters in blue and 1 meter in red. So you can see that without sea level rise in Macau, in this area for 1 meter, without sea level rise, the return period will be 960 years. But if we have sea level rise for 50 centimeter or 1 meter, the return period can be reduced to 800 or 460 years, like that. So this is how also another dimension or another way how we can interpret the impact of sea level rise on tsunami. So by that, I would like to, sorry, it is quite rushed, but I hope you can see more detail in the chapter. But I would like to summarize that Again, as I mentioned at my early slides, that there are quite several structural measures like seawall and breakwater that have been used implemented in Japan, but again, before 2011 we had overconfidence, but now after 2011 we realized our capacity, and we try to change the way of design to the level 1 and level 2 based on the return period of the tsunami. And the second point is that again, related to level 1 and level 2 tsunami, we would like to make sure that the height of our defense should protect high frequency tsunami, but for low frequency tsunami we should have enough countermeasure, evacuation and countermeasure, and we have to merge or combine with other land use planning or non-structural measure as well. And I also mentioned about now Japan invests a lot on sensors for both earthquake and tsunami. So this kind of sensor can also help increasing the accuracy of the tsunami warning and also support the evacuation processes. And also, I also show some example that we merge, we add zero rise in tsunami simulation, and we can see here in that depending on the local topography, that the maximum run up can be double of the sea level rise as well, or the inundation this time will be increased, or in some case it will be roughly 20% of the inundation area. Last but not least, so we would like to propose that policymakers should also keep in mind about this kind of influence in the future when they plan for the tsunami mitigation in the future. Thank you so much. I think I'm not over the time, and I would like to pass to the closing.
Thank you very much, Anawat. You're right in time, and I take this opportunity to thank the three speakers, Alastair, James, and Anawat. Thank you very much, because your talks were very interesting, of course, but also because you were fully in time according to our expected timeline. So I might take this opportunity to say once more that if you have any question to the speakers, we have no time to answer the questions right now, so please write your questions in the chat window, and the IAHR Flood Risk Management Committee will manage to answer your questions on their website after the webinar. Also, that this work was sponsored by Hydra Software Limited. And I must say a few words about the technical content, maybe. I was not part of this work, but I'm interested in funding risk, as most of the attendees of this webinar. I'm very happy that the speakers have used some real events to illustrate their advices and practice advices. So it is, of course, the case with the last speaker who used the Tohoku tsunami as an example. Also, for the river flood risk, we have in mind the importance of the climate change effect on the engineering practice to design and mitigate when we talk about flooding. And this is a very important topic, of course. In Europe, for example, right now, we know that Spain is facing particularly terrible flooding events near the region of Valencia. So I have no doubt that this monograph will be very useful to researchers and engineers. And this is nice because IAHR is happy to contribute to the dissemination of knowledge from researchers to engineers, because mankind is now facing some important risk due to flooding, either on coastal regions or near rivers. So with that, I think it is time to close this webinar. Thank you again to the speaker. Thank you, Estibalis, for organizing this webinar, and thank you to our audience. Don't forget to ask your questions through the chat window, or if you don't have time, you might maybe send a message. Is that possible, Estibalis? Do you think we can also accept questions through your
can
email
collect
address?
them, yes, and they can send any query to publications@IAHR.org, and they will be collected and answered in the next weeks.
Okay, thank you very much. So have a good day, night, or anything according to the place you live on this earth. Thank you very much. Bye-bye.
Bye.
Bye.
Thank you so much. Bye bye.